everyone, it's Judy Warner. Welcome back to the Ecosystem Podcast. Well, this is a very special week, and I am so excited to bring you 5 straight days of podcasts that I'm calling the DesignCon Tailgate Party. Basically, we're going to be pre-gaming with all the superstars from DesignCon, the names that you know, the leading companies, the iconic speakers, and we're going to be talking about everything that's being presented and brought at DesignCon next week. I will also be there podcasting on the show floor, so if you're going, I hope you will stop by my booth 1108, and our sponsors have given us lots of great giveaways, including signed books by Steve Sandler, a Keysight backpack, a handheld Siglant, oscilloscope. So please be sure and see me. Today on day one, I bring you 3 superstars of DesignCon: Steve Sandler of Pictotest, Heidi Barnes of Keysight, and Ben Dannan of Signal Edge Solutions. We're going to talk about VRM modeling for power integrity engineers that is accurate, easy to do, and blazingly fast. I think you're really going to enjoy this, and I will put the links below for their paper, and I hope you can attend in person. Now let's jump right into this conversation with Steve Sandler, Heidi Barnes, and Ben Dannan. Hi, everyone. Thanks so much for joining the podcast today. Steve, let's start with you. Will you please introduce yourself to our listeners and tell us a little bit about you and the organization that you're with?
Sure. So I'm Steve Sandler. In case the white beard didn't give it away, I'm old. I've been at this game a very long time. So I've been involved in power electronics since the 1970s. First project I got to work on was the space shuttle. So I've been in the space business for most of my career, and now I am the founder and CEO of Pictotest, the company that makes test equipment.
Ben, how about you?
Hi, I'm Ben Dannan. I am a technical fellow at an aerospace and defense contractor, and I have my own consulting company, Signal Edge Solutions. I focus on system-level power and signal integrity. I work on next-generation ASICs, high-end FPGAs, and I model those end-to-end.
Heidi?
Yes, great to be here, and thank you, Judy, for letting us have this opportunity to talk about power integrity. My name's Heidi Barnes, and I am the Keysight Power Integrity product owner for our simulation software. And I have a long history in signal integrity, but since I met Steve Sandler, I've been fascinated by power integrity, and that's my main focus these days. Doing a lot of collaboration with Steve and learning at the same time from his years of expertise in the power electronics and power integrity industry.
Well, I think we all have that in common. We meet Steve and we go down some crazy path together. But, you know, the reason I brought you all together here is because you're doing a really interesting talk together along those lines. And so I wanted to give our listeners a little preview into that. And the way I first met Steve and Heidi was going to a boot camp at DesignCon, which was very, very popular. So Steve, Heidi, why don't you tell our listeners a little bit about your boot camp and sort of how you came together in that way around power integrity, and then we'll weave Ben's story into
Sure.
today's episode.
Why don't you start off?
I still remember that Steve had this square printed circuit board. He stuck a connector on it, and it had a power, basically a plane of copper on one side and a plane of copper on the other side. So one was the signal power plane, and then the other one was the ground plane. And he put a connector on it, plugged it into a network analyzer, and then challenged the EDA simulation companies to, simulate what the impedance was.
That's right.
It should be a simple simulation. And he was frustrated because it turned out to be not so simple. And so that was where our collaboration started. I was able to get that into our ADS simulator and get some really good results on impedance. And that then, we met through DesignCon Technical Program Committee. And that just snowballed. He was very excited about using ADS and all the things that we could do, both from sort of a SPICE level transient AC simulation world, all the way to the EM sort of digital twin type of EM models of the printed circuit board and get those very small parasitics. So, and then, obviously the best way to train the community out there is to have boot camps. And I think one of the biggest challenges we've had with power electronics and power integrity is everybody thinks power delivery is easy. It's DC. It's low frequency, and they want to just leverage from a vendor. The vendor says the power supply puts out 1 volt. Good. We'll just stuff it on our board. And it's not easy. Power delivery is AC, not DC. And so we're having to really educate the community on the need for simulation to understand those parasitics and how it impacts your design, and that you shouldn't just leverage things. You should actually be a power integrity engineer or a power electronics engineer and design things and use the simulation tools to really engineer the power delivery from the voltage regulator all the way out to the load. And
Right.
Steve, you can add to the comments there.
No, I think that was a really great summary, and it's been a lot of fun right from the time Heidi and I met. And it's true. We did this little double-sided board, and it was fascinating to me that only 2 simulators got the right answer, and ADS was one of them. And I was already invested in ADS. I decided I was going to learn RF and microwave, and so I had a copy of ADS, and I was learning it. I was even writing a book on RF for power engineers that I never finished. But we kicked off this boot camp. I think the first year we did it was in 2016. And we had no idea how many people were going to show up for it. And we were in the room. It was upstairs at DesignCon. And we looked out the door, and there was a line of people that didn't register for it, but they wanted to try to get in. And we were like, holy cow, we might be onto something here. And so we've been doing it ever since.
Well, I remember popping into your class a couple of times, and it's literally standing room only. It's every engineer's got their laptop open, and you guys go deep in the weeds. And so you could tell everybody was just eating it up. So I always knew it was one of the most popular, which is how I sort of ended up reaching out to Steve, and then Steve introduced me to Heidi. So that's how we were brought together. And then Ben, we worked together briefly through Altium, and then got to know him. And then he was writing papers at DesignCon, so I was kind of supporting his journey. And then he was learning ADS. So this is how we all found ourselves together. And now, Ben, you are part of a new boot camp. So why don't you tell us about the title of your talk? And it sounds like you were actually the one that was kind of poking around and pulled these two into doing sort of a fresh spin on a topic around power for this year's DesignCon.
Yeah, sure. So I'm doing a boot camp called Memory Design Fundamentals for Next Generation Memory Systems. It's with a bunch of great colleagues, Randy White, Saeed Savant, Herman Ruckerbauer, and Hee-Soo Lee. But how this whole thing started with Heidi and Steve, we've been writing and publishing together now for a little over almost 2 years, done some media icons together and had a lot of fun. And I'm just grateful to get to work with them and collaborate, like Heidi said, right? So I just love working with these guys, and it's so much fun to work with Heidi and Steve and grow and learn and share knowledge, right? Because at the end of the day, that's what DesignCon's all about.
Yeah.
And so this really came about because where I work and what I do from a modeling perspective, we need to know what the voltage is going to look like at the die bump. So we include the substrate or the MCM package, whatever terminology to use, the board, and everything to the VRM. And so that means we need to have a good or a strong VRM model to ensure we have the right answer. And so out of need, I had to teach myself and work with Steve and Heidi to learn how to build what we call Steve's model, right? We call it the Sandler state space average model because this is really Steve's legacy. And it's in his book, Power Integrity ADS, which is a great book. However, there are some things that aren't in there. And so Steve is so brilliant, and there are steps that we find sometimes get skipped, right? So you have to connect the dots. And so, And so I had to kind of pull it out of Steve in pieces, or just kind of grind on the old grinder stone there to figure it out. And so
Well, that's
that
well
was,
put. That's well put. I left a couple of fragments out.
and so the whole process came about for me learning. And well, I created the model and was working with Steve to share it, and we wanted to correlate it. And where this whole thing kind of came about was I showed the results to Steve and Heidi said this would be a great paper. And when I pulled in the board effects, because the measurement didn't match simulation, and so the first thing I did was I pulled the board effects from TI, Texas Instruments, and that's our fourth author, right, Christian Yachts. And so I asked Christian, I said, hey, Christian, can you give us the board effects? So we worked with him, and that's why we brought him on the paper, so we can all kind of collaborate together. And as soon as you pulled in the board effects and extracted that and added it to the state space model, boom, there was the answer. It matched verbatim the simulation. And that's really how this whole thing came about.
Yeah. And that's where you get insights. That's where the engineering insights really come from, because now you can really understand what's controlling the performance. So it's really fun to watch Ben go through that whole process there, and the great results that he got.
Yeah, for
Yeah.
sure.
So, Ben, you mentioned Sandler's Legacy with the state space average model. Steve, why don't you give us, tell us what that is and how that came about, and then tie it into how this ended up being part of this paper.
So this model is really old. I wrote it in the 1980s, and we were doing simulation in the 1980s, but it wasn't very good. And I was looking for models, and I couldn't find one that actually did all of the things I needed. Specifically, I needed one that could do different modes, like discontinuous mode and continuous mode. That's how I wrote my own. And I published a book about it in I think it was 1995. I published this book, and it became really popular. They even translated it into Chinese, and it's been really popular. And I think it was around 2006 or 7. National Semiconductor called me and they said, we have this crazy idea. We want to run simulation over the internet. And we can't get it to seem to run fast. And of course, we didn't have gigabit internet either, right? I mean, it wasn't quite dial-up, but it wasn't fast internet. Right. And so they said, we need simulators that'll run really fast over the internet. What could you do? And so I came up with this idea that would use the state space average model I wrote in the 90s that's really fast. And we would use that to figure out what the switches would be doing. And so the switches just copied what the state space model would do. And that way we didn't have to calculate all these node steps and all these step points. It could just turn switches on and off when the average model told it to. And that worked pretty well. We wrote a paper about that with National Semiconductor, I think in 2008. And then I think it was around 2015. I said, if I could manage to get this to run in harmonic balance in ADS, that would be amazing. Because then it would be naturally Fourier based, and we could do, spectral plots and ripple and time domain reconstructions and everything. And it would be even faster than what we did for National Semiconductor. It was more than 10 times faster. And so, Ben said that, he likes working with us because we learn from each other. He likes working, with smart people. And one of the things I learned is we're all smart. I mean, we all know different things, but we're all smart at what we know. Right. And so when we get to work together, it's just so synergistic. Everybody brings something to the party. And so I showed Heidi this harmonic balance thing. And of course, she came back and said, oh, you mean like this, right? And she cranked it up 10 notches. And that's how Picotest works too. We have our manufacturing partner in Taiwan, and I draw a little schematic. I make a prototype. I send it to them. I said, I need you to make that. And they send something back, kicked up 10 notches. And they said, you mean like this, right? Of course. Yes, exactly. Just like that. And so I think that, what we're doing here is we're all having fun. And we're learning from each other, and we're learning about sensitivities to the different problems that we have. And Ben is right. One of the things that I get from working with other people is that we do have all these little gaps in things that we share. And I think it's partly because we didn't think we needed to share that. Everybody knows that, right?
Right.
And so that's just this minor detail. But no, not everybody knows that. And so when you get to work with other people, And then it's like, yeah, Ben, pull those fragments out. We go through the process end to end, and now Ben has perfected the use of this model, and it's interesting to me to see that 32 years later, it's still a good model. It's still a valuable model, and it does so much more than I ever intended. And I think about Dr. Nagel, when he wrote Spice, and I mean, if he could see what Spice is today, he would be absolutely shocked because this isn't what he thought, right?
Right.
And so, how did it become that? And so, I think that's kind of where we are, and I'm having so much fun watching what it is that, a program like ADS brings to it, where all of a sudden we can simulate EMI in real time. It's like, wow, holy cow. And at the same time, it also puts a lot of pressure on young engineers because now they have these new tools and they could do even more than they could before, but they didn't get more hours in the day. So,
Yeah.
so one of the things that we're constantly working through is, where do we focus our time? What do I really need to know? And I think that's why people like our boot camps and stuff.
I think
There's
so.
a shortage of that core information. And, the questions I get all the time are, what do I really need to know? I know that there's a lot of details, but what do I need to know? And that's what they want to know.
Well, I was speaking with Matt Burns from Samtech, and we were talking about, if you can believe it, 224 gigabit per second flyover cables. And I'm like, wait a minute,
Yeah.
what happened? Like, just not long before COVID, we were like, maybe we could hit 112. And I'm like, how did that happen? And we had an interesting discussion that you're making, actually, all of you, in a different way. And that is the speeds and the performance. Our time is more constrained, and we all have these little pieces, which is why the problems I could see engineers having is there needs to be an ecosystem. Like, it takes an
For sure.
ecosystem of knowledge, people, disciplines all coming together to to figure this stuff out. And so I love that you guys are just like a little ecosystem of, you know, TI,
Yeah.
Keysight, power integrity expert,
Right.
prime, high end engineering. And so it's great that coming together, you've been able to sort of, tell this technology story and then put that in the hands of engineer. And, what perfect place besides DesignCon, right? Which
Yeah.
is
Oh,
really
yeah.
what it's all about. So you guys have taught me a little bit about models, and you've mentioned RL, RLL, VRM. Like, what's the difference? So you're talking about VRM. What's the difference? Ben, you want to unpack that? Who wants to unpack that?
Sure. I mean, that's the whole premise of our paper, right? And so the whole idea is we take Steve's model and we show why you care about, first off, using a state-space average model versus a SPICE model. And the second part that we talk about is why you want the board effects. And we show correlation to measurement, and using the Sandler state-space average model with the board effects, not only is our ripple dead on, but even the ringing in the ripple to the simulation is dead on. And we go a step further and we show with a step response where we create a fitted SPICE model and do a step response to that versus the state space average VRM model, what you're losing, right?
Mhm.
And we show that with and without the board effects and look at that from a spectrum perspective. And that's really the meat and the value of the paper. The really two key takeaways that every engineer should walk away with is that if you're doing power integrity modeling, right, the VRM doesn't stop at the VRM, right? That's the gap and delineation in the industry with power electronics and power integrity today. Power electronics engineers will design a VRM and say they're done, but they don't include the board effects. And so the
Yeah.
other side of that coin is on the power integrity side, which is a battle that Steve's been fighting for a while with Heidi, is that you have the SPICE model. And so you don't get all those noise sources, and I'll let Steve talk about that. And so we want to include the board effects, and you want to use a state-space average model, and that's how you get the right answer. And that's the two key takeaways you want to have from this paper.
Yeah.
Okay.
So our focus, has always been on why it is that it's so important to consider end-to-end simulation.
Yeah.
When I first started this business, my boss said, nobody's ever going to think your power supply is sexy. You're never going to get any credit for doing anything. Your whole job is to make the load look good. And, today, I dare say 45 years later, It's a little bit different. You talked about 224G, and yeah, we did get there, but getting there, they also realized that the power supply matters. And so in the new QSFP specification, you'll see they have power supply noise requirements, and everybody's sitting and looking at each other saying, we know how to make a 224G transceiver, but we don't know nothing about power. So they wrote this spec about how they would test to make sure that they had power supply robustness, except they wrote a spec that nobody could meet. And so finally that ended up on my desk, and they said, could you build a modulator that could test a 224G transceiver? And so you'll see we actually have a tutorial about that at DesignCon, but everybody is learning that, hey, we can't just ignore the other guys. We're all on the same board and we're all talking to each other. And so whether you're a high-speed guy or an optical guy or an RF guy or a microwave guy or a power supply guy, we're all on the same board. And like it or not, we're all talking to each other. And so it just doesn't make any sense that you would do a simulation that ignored everybody else. And that's what happens when you look at the RL or RL models, is that you've ignored the fact that everybody else exists. The frustration has always been that the people that design the power supplies, the actual power electronics guys, they seem to be allergic to power integrity. They don't really understand it. They don't really want to understand it. And so, like you said, what a perfect place at DesignCon. But power electronics people aren't there. Power electronics people are at APEC. And so this year, for the first time, the three of us are going to get to promote power integrity as a tutorial at APEC, where we get to talk to power electronics engineers and kind of try to bridge that gap. But if you go on any one of the forums from any one of the semiconductors and look up, the models that are coming from the vendors, every one of them says your simulation's not right. Your models are terrible. The results don't correlate. And it's like nobody understands or nobody cares or something, but the right answer matters. And so that's what we're talking about at DesignCon, why it is that this model is important and what it is that it does. But also, hopefully, we're telling them that it's not hard and it's not a lot of work. We made this really easy. All you need to do is plug in a couple of numbers in my template and you'll get the right answer. We minimized the work. And so hopefully we get that across too.
I imagine when I listen
I would have
to
to say too, we're engineers, is that it's interesting to me that how many electronic engineers don't want to deal with a control loop. And yet we all had that in college, control loop theory and stuff. And yet here is a very simple control loop. And state space modeling is nothing new. It's a very old technique. And so, Steve has shown us that here's a fairly simple state space model of a control loop to model those two different states, state one and state two of the switching for the switch mode power supply, your switching pulse width modulation. And yet it's interesting how many people, don't want to have to learn about how the control loop works. They want to just put an RL model in there. And so I think, people shouldn't be afraid of it. I think they should take a look and realize how simple it really is to have this state space model that provides your control loop feedback so that you can really look at what is the bandwidth of your power supply. And Steve was mentioning the power electronics engineers don't want to know about power integrity. Well, it's fascinating working with Jack Carroll of Xilinx with some of our previous papers. We finally came up with a graph that shows going from low frequency to high frequency, that at very low frequency, the VRM is delivering power. Well, your VRM vendors, that's all they want to talk about is that lower frequency range. But my device is running at gigahertz.
Yeah.
And, how do I get, power to the gigahertz switching device? Well, the VRM can only go so far. And then there's a center mid-band frequencies where the printed circuit board decoupling capacitors are actually the power supply, the charge delivery. And then if you go up high enough in frequency, the third range, the printed circuit board decoupling capacitors can't get charge or current into the package fast enough. There's too much inductance there. And at DesignCon, there's they call it the Bandini mountain of inductance, because there's only so many power and ground pins. And so there's an inductance there that prevents, getting power in at higher frequencies. Well, then it becomes the package and die capacitance to deliver that gigahertz switching current. And you really have to look at that whole ecosystem. How do you transition from the VRM to the printed circuit board decoupling to the package die capacitance without having resonances? I guess Steve loves my term of sloshing of current back and forth between inductances and capacitance and creating resonances.
Yeah. So in 2018, Heidi and I added Jack Carroll to our boot camp. And it was fascinating because Jack is another brilliant guy, right, from Xilinx. And certainly he knows FPGAs better than anybody on the planet, for sure the Xilinx FPGAs. And yet ran into this problem that turned out to be a simple power supply problem. And so here, he had this great 56 gigabit board, and it was working great so long as you didn't have to turn the transceiver on or off. But as soon as he turned the transceiver on or off, then he exceeded his noise levels because of the power supply. And it turned out also because of board connectors and stuff. And it was just so mind stretching, I think, for Jack. And then we did 3 more papers, I think, with Jack, 2019, 20, and 21. And it was amazing that by 2019, he had already had this mastered. And by 2021, he was making GUIs for Heidi so that Heidi could prove the stuff that she did was right, even though we couldn't measure it inside the FPGA. And it was just another great example how when you put these smart people together, it's like, holy cow.
Yeah.
But Jack, as brilliant as he is, and he's focused on this 56 gigabits, it took a while to wrap his head around how it is that a connector on his power supply could cause this problem and bring the system down. And so it's just fascinating, but it's another example of why this end-to-end stuff is so important and why it's so great that when we get to work together with these people.
Right. Well, Ben and I had done an interview, or we had a conversation together about power electronics and power integrity, and I thought it was really interesting. So I'm gonna, along those lines, right? Ben had said to me, well, the power electronics, it doesn't stop. And then we go over here and take a look at the power integrity. Like they're connected, they're not, it's not throw the thing over the wall anymore. But in regards to both Christian and Jack, right? And you guys have all taught me, but I want our listeners to hear all 3 of you, and I'm going to start with Ben, explain why engineers just can't simply use the semiconductor manufacturer's data sheets and just plug in the numbers. Why? Why can't they just do that, Ben? Works, right?
Oh yeah, I mean, who do I quote here? There's lots of people you can quote. Steve's a good example. Heidi, even Lee Ritchie has said. I mean, a lot of times these data sheets are made by, unfortunately, marketing folks, and they don't always represent everything the part is capable of or can or can't do. And so there are errors in those data sheets. I can tell you from experience, I've gotten models that are wrong from all the big IP semiconductor and silicon vendors, and had to work with them to go back and forth to fix them. These simulators, like Heidi said, are going to do what you told them to do, right? They're going to give you the right answer based on the models you put in there and how you set it up.
That's true. Simulator's always right.
Exactly, right?
It's just the question that was wrong.
Yep. Yeah, we were talking about that, where you put something, you push the button on your simulator, and you can push it 100 times and you get the same answer. And then you go over to the measurement bench, and you take your measurement and you hit save, and then a couple minutes later you take the same measurement, you hit save, and it's different. And so then you're hitting the button over and over and over to try to see, okay, did I get am I getting the right answer? Yeah. And it reminds me of a saying that I heard at DesignCon at one of the panels, and it was basically that nobody believes the simulation except for the person who did the simulation, and everybody believes the measurement except for the person who made the measurement.
That's
And so
probably true.
I working with Steve, I think that's one of the best things about his state space model, is it's a measure-based model. It forces you to really go and measure things, and you really need the combination of simulation and measurement
Mm-hmm.
to make you honest and to really make sure that
Right.
both are giving you valid answers and going, and that you have a robust model, that you have a robust measurement process. And I have to say, to your question, when you buy a electronic part, a VRM, and you're looking at a data sheet, there's a lot of risk if you don't, go test or measure what you bought. So there's a lot of benefit, a lot of learning from just going and making sure that what you're paying for is what you're getting, and that's what this Sandler state space average model forces you to do. You learn a lot about measurement, and you learn a lot more about how that device really works.
Well,
My
and there's
experience
people
tells
like
me that.
Ben right in the middle of that, right? To me, there's
Right.
working
Yeah, for sure.
engineers just scratching their head. So what I love
Yes.
about the three of you, and even having Christian in this conversation, like you've said, it's the ecosystem of knowledge putting together. But at least with the state space average model, at least you kind of have a single source of truth, like, right? And then, but Ben, you've taught me about correlation, right? And how important that is. So
Oh,
what are
yeah.
you going to
Yeah, I
correlate
learned from Steve and
against?
Heidi, honestly. I mean, they're the ones that taught me.
So,
So, I mean, of this model, I mean, what are you, what's the question? What are we going to correlate against with this model?
yeah, that was the question. Like, well, how can you get accurate correlation if you don't know the model's good and it's in the right, what are you measuring? And
So that's where we talk about that whole thing in the paper, right? I mean, Picotest makes the injectors. You can make the measurements, bring it into ADS, and use ADS, right? And folks like Heidi have set it up where it's easier today than it's ever been. You just have to follow the steps to bring this model in and tune it to what it's really doing in real life.
mm-hmm. And Heidi,
Right.
well,
Yeah.
I interrupted you, Steve. What were you going to say?
No, I was just going to agree with Ben and tell you that my experience is that, most of the time when we don't have good correlation or if we have bad models, it's usually that the vendor's data was poor.
Mm.
And there's two reasons for that. One is that they don't really have the expertise to make the measurements. And so they're often very poor fidelity. And often when they get to the higher frequencies, they just kind of write off things that they see, but they don't really want to see. There's this psychological part of it too. And so very often in satellite systems, when we find problems in the system, it's in the data sheet. The data was there. Just nobody understood what it meant, and everybody ignored it. I'm on a panel with Isvan Novak, and we'll talk about that in that panel. But his question was, what do we really need from their simulators? And I said, confidence, right? We need confidence in it. That's what we need.
Yeah.
And so I think, when you've made enough measurements and you've done enough correlations, you get pretty good at it. And I think one of the most important things is to recognize what bad data looks like. And if you go back to your roots, we learned about control theory, what do poles look like in a graph and what do zeros look like in a graph. When you look at these graphs, they don't do that. There's got to be bad data here because poles and zeros don't do that. And I think unless you get that foundation set, you're going to have trouble with it. And so I think a lot of this stuff that's done at the semiconductor companies is a little bit on the mindless side. And it's people, like Heidi said, they're sitting there pushing a button and whatever came out, they just put it on paper. They didn't question whether or not what they got was good, bad, or indifferent. They just put it on the paper.
Which I've heard Heidi, you and Steve talk with Eric Bogatin, about this, and it's like, is it this or this? And you all go, it depends.
Exactly. Exactly.
And so, yeah,
Mm-hmm.
it's so I love that, and I think you're doing a lot to teach engineers like Ben,
Well, I
and
think
maybe so many that are less experienced. What about the up and comers? And Heidi, why do you think engineers are hesitant about the control loop?
it's just we have a lot of things on our plate. It does take there is a little bit more complexity, but again, it's, if you really are a power integrity engineer, it's part of your job to understand how that ecosystem works. And so, again, it's, I think, I actually, if I look back at even SI and now it's more PI recently, the first time I start looking at something, and the two-port shunt impedance measurement is a great example. The first time I looked at that measurement, I had a really hard time understanding how you can connect port 1 to port 2 and put a shunt in the middle and turn it into impedance. And but the more you do it, the more you look at it, the simulate it, you measure it, and the more often you do it, and like what Steve was saying, the more you look at actually what the data is supposed to look like, you get a lot more confident. And then pretty soon it's like, why can't that person understand this? Why? I told him, it's this really simple measurement. Why is it so hard for them? And you forget how hard it was for you the first time you looked at it. And along those lines, we actually have a chip head theater one. Steve and Ben and I are teaming up, and it's hands-on power delivery network impedance and calibration basics. And so we're doing this PI hands-on two-port shunt measurement technique, and we're hoping to figure out how to give it, this explain it in a simple way and make it easy for attendees at the conference to go and repeat it in their lab and become experts at measuring impedance. And then I think we're followed by Eric Bogatin, and he's going to do an SI hands-on.
I think it's an important focus, is to try to get this to be, simple enough that people can grasp it, and simple enough that it doesn't become yet one more major task for them to try to fit into their busy day, right? It's just what matters. One more thing I'll say about this model: when you make this measurement-based model, you actually learn a lot from doing it, because you're constantly adjusting these parameters to figure out how it is that you get the model to match the data. And in the process of doing that, you build this intuition that says, oh, so now I know what that parameter does, and I know what it looks like in the measurement. And then all of a sudden you realize that you can go look at this measurement and say, wow, the ramp is too big. And it's like, wow, where'd that come from? I mean, I know I just said that, but how did I know that?
Right.
And you knew that because you get this experience of you're moving this VRM slider up and down and you're watching what happens. And so I think that it builds this intuition that makes you a better engineer.
Well, and I think, engineers do their best work by touching things. At least that's my pushing buttons, even if they're wrong ones. But then that's how that sort of gut level, visceral intuition comes into play by just doing that enough, right? It's just another skill. And for our audience, I want to tell you that all three of these people, why I wanted to have them on podcast day, because they're all presenting. I think Steve's got 4, Heidi, I don't know how many, Ben, you have at least 2 or 3. So I am going to put, you are, okay, so I'm going to put the link to the DesignCon schedule. You can look it up by speaker name, and you can find everything. And on Steve, I'll link to, I think you said that Picotest has a DesignCon page, right, where your things, and Heidi, does Keysight have one of those too?
I'll have to check, but we do have a Keysight education forum where I will be doing a power integrity presentation. What is it? Advanced power integrity simulation and measurement methods. And DesignCon usually publishes that along with their regular agenda. So that should be up there on the DesignCon website.
All right. So because there's only so much we can do in 30, 40 minutes, I wanted to let our users know they can go dig into all that, because, this sounds like a fascinating paper. And what I really like about it is you're all separately sort of getting to this place, like it's not as hard as it looks. It's not an intimidating, and that you've worked together to sort of crack this problem to make it more accessible by you. And so I think that's a really exciting message. So best of luck to you guys. I'm sure this is going to be a great, great session. And will the paper be available publicly, or is that only for DesignCon attendees?
So that's a really good question. So first, let me tell you that they did tell us they're recording it. So
Oh,
it's going to
okay.
be, so it's going to become part of the DesignCon virtual. I
Okay.
do believe that this will be respun into a paper. We're not allowed to share the DesignCon paper for, I think it's 6 months that we're not allowed
Yeah.
to
Yeah,
share.
there's usually a delay, and then we
Yeah.
can share it after that.
And we can, but I think we're actually going to be doing this at another conference and spun in a little different way. And I've also presented, similar papers in prior conferences. So there's plenty of information here that's available if people want it.
And we did add it to our tutorial for APEC because it makes a nice complement of Power Integrity
Okay.
Basics tutorial and doing the whole ecosystem simulation.
Yeah.
Yeah.
Well,
If you
so
want, we
the
can
rule
put,
is go to DesignCon. Don't miss it.
Yeah.
Yeah.
That's the
Yeah, if
bottom
you want, we
line.
can put together some links to the other relevant
Okay.
papers that
All right.
your listeners might be interested in.
Okay. Well, I'll make sure. And I know Heidi sent me something. Was that the link that you sent me, Heidi, was on the one that you mentioned? Or was that
Well,
on something else?
APEC is March 19th in Orlando, Florida, so that's a different
Okay.
conference for the
Okay.
tutorial.
Okay.
Like Ben mentioned, we gave him the premium tutorial slot, and he's doing memory design
Yes.
simulation and
Yeah.
measurement stuff. So I think we're going to take PI to APEC and hopefully educate the power electronics world this time or this year in 2023.
Okay, well, I'm looking forward to everything you guys are doing together, and I really applaud you for this amazing collaboration that I think is, not only fun for you, because I know you're all a little, engineering in the brain. I know it's fun for you, but also I think it'll be so valuable to other engineers. So thank you, all three of you, for all you do, and thank you for coming on and sharing it with other engineers. I really appreciate each one of you, and I appreciate the three of you together. Thanks so much for coming today.
Thanks, Judy.
You bet.
Yeah, thank you, Judy.
For our audience, make sure you go in and dig into the show notes. I promise before I publish this, I will get lots of good stuff put in the show notes for you so you can link through and access as much as possible if you're not able to attend. If you are able to attend DesignCon, they've been very, very gracious to offer 20% off all of Ecosystem listeners by just using the promo code Judy, all caps. So if you haven't already bought your ticket, go over there, use my promo code, and I hope to see you at the show. Until next time, always remember to stay connected to the ecosystem.